In the last couple of lectures, I showed you what's the effect of electron donating or electron withdrawing group. We said electron donating group will technically lead to the ortho or para position, while electron donating, they will favor the meta position. And in this case, I have a substituent, and the substituent is methyl, and I'm treating this technically a toluene molecule with nitric acid and sulfuric acid, and this is going to be nitration. First step of the reaction is going to be generating electrophile, and our electrophile is NO2 with a positive charge or +1 charge. And we need to answer two questions: whether the reaction is going to be faster or slower than benzene molecule, and the second thing is what's the ratio of the product we get? Do we get one or more than one type of products? Okay, so first step of the reaction, as I said, creating electrolyte and electrophile, and the electrophile might be added to the ortho position. If we add it there, then we will have a positive charge close to the methyl, and that's going to be the best case. Why? Because the methyl or alkyl group, they can only help to reduce the positive charge through induction effect. That means they need to be too close to the positive charge. The further the positive charge is from technically the alkyl group, the harder will be to stabilize it, okay, or to distribute that positive charge. And clearly, we have hydrogen also here. Okay, that's one case. If we attack the methyl position, the electrophile, it will be here. Hydrogen is going to be there. The positive charge, it will be in this carbon. And if we attack the para position, the electrophile, it will be here. Hydrogen attached to the same carbon. Now we have a positive charge there. Okay. Question is, which one of this is the best carbocation? Okay, and or let's put it this way. Okay, the lower the activation energy is, the faster the reaction will be. I have three carbocations. One, it has a positive charge close to the methyl. Close to the methyl, it looks really stable. Next one, is way far from it, but it's in the positive charge in the para position. And last one, positive charge in meta position. Okay, now the first one we got it through technically ortho attack. This one is through meta, and last one is through para attack. Okay, now let's talk about the how stable these carbocations are. Okay, now the first case is through ortho attack. If we get it through if we add it through ortho position, we'll have the positive charge close to the substituent, close to the methyl electron donating group, and that's fantastic. Okay, next one is if we add it through, let's check this time, the para. If we add it to para, now we will have a positive charge here, positive charge there. It looks as far from the methyl, but we can move these two electrons. If we move them here, now we will have a double bond there, and the positive charge is showing on a carbon that it has the methyl substituent. Again, this one looks similar to that. Positive charge is sitting on a carbon that we have electron donating group there. Now, when it comes to the meta attack, okay, it doesn't matter really how you move the double bonds. You cannot put the positive charge on this carbon under any condition. Positive charge is not going to show up there, and positive charge is at least 2 bonds far from the substituents. Okay, again here 1, 2 bonds, and this one 1, 2, 3, 4 bonds. So it's way far from it, and because the distance between the substituent and the positive charge and is longer, we will say it will be harder to stabilize carbocation that we got it through meta attack. So meta attack, it will be the worst one. Okay, that one it will be the worst one. And what's the best condition? The best condition either ortho or meta. Now, before I show you the product, I have to say this: the meta, when you the ortho, when you add the ortho, yes, it gets stabilized through putting the positive charge on a carbon that it has the substituent, but it's going to generate this. It's going to generate some repulsion between the methyl group. Well, on this one, the para, they are way far from each other, 180 degrees far from each other. And so I'm going to say the para position does not have a steric effect. We are not dealing with this one, okay? So I'm going to say no steric effect when it comes to the para attack. So para attack should be the most favored one. And yes, the para is more favored because it doesn't have a steric effect. So what's the product of this reaction? I'm going to say the product will be this. Okay, we will get mainly the ortho plus the para product. This one, it will be NO2. Okay, how about the meta? Meta, it will be really, really small number. And again, this one is going to be ortho, and this one, it will be the para addition. Okay, so I said para is the major one, ortho it will be the second, and the last one it will be the meta. And you might get something from meta, but really minor one. Okay. Now, if you replace a weak activator like a CH3, but by OCH3. Okay, OCH3, because oxygen it has 2 lone pair, that's going to be a strong activator. So it's going to be way, faster. The reaction is going to be way faster than a benzene or toluene because it has the lone pair. Not only through induction effect, it can stabilize the positive charge, it can share the lone pairs with the ring, and that's going to stabilize stabilize the negative charge, the positive charge on the ring. Okay, and now we have 2 facts here. One, we have an electron donating group. It can donate electron through induction effect, and it will increase the density, or it can share a lone pair with the ring. And if that one happens, as you see, we are getting negative charge on ortho position, okay, negative charge on para position, and negative charge again on ortho position. Now, check the meta. We did not get any negative charge on the meta. So now when the electrophile, whatever, in this case is going to be Br plus. When electrophile is reaching the ring, it can see a good amount of electron density on this carbon, okay, either of those ortho carbon or on the para position. So the attack is going to happen here on ortho positions or a para position. Okay, wherever we have a negative charge. Remember, Br comes with a positive charge, is looking for electron density. Okay, so now when we add the Br plus, if you added it through the ortho position, you will get the Br here, and this is going to be ortho, or it can be added through the meta position, so through the para position, and then in that case we will have para, bromo, anisole, and still this product still is active enough. Why? Because it has 2 lone pairs on oxygen, and the reaction is not, in fact, it's not going to stop here. If you add excess of bromine, reaction is going to go 2 steps more. Okay, 2 steps more, and regardless of whether you have ortho product or para product, it will turn it it will occupy technically any ortho or para position. And so if you have ortho, for example, you had the ortho, it will add 2 more bromides, one here, and next one it will add it there, until you get technically tri-bromo anisole product. And again, with the para, same story. With the para, we have 2 ortho position are empty, and if we have access to bromide, and the excess of bromide are there, then the bromide is going to technically attack those 2 positions, and it will occupy them, and we will have 2 bromide on the ortho positions. Okay, now I'm going to practice another example, and in this case we are doing nitration, and we are adding nitric acid and sulfuric acid to anisole. We said again, an anisole, because of oxygen with 2 lone pair, is really active and is 400 times maybe more active than benzene ring. And first step of this reaction is creating an electrophile, and the electrophile it will be NO2 with a positive charge. Okay, and so we get meta, para, and ortho, meta, and para. The para, it will be something around 60%, and while the ortho is around 31%, while the meta it will be around 2%. Okay, now why then para is way higher than the ortho? Well, we have 2 ortho position, so technically we can say we can get the ortho product from 2 places. We can add it here or there, so our chance should be higher. The reason behind it is the steric effect. Okay, the steric effect is higher when it comes to ortho position, and while the para position does not have that like a steric effect, so in addition it will be faster when it comes to para position. Okay, again we have NO2, it can be added to the ortho position. If we add it to the ortho position, we'll have a positive charge on carbon where we have the CH3 there. Okay, now this one very soon it can stabilize. It can stabilize the positive charge through sharing a lone pair. Okay, sharing a lone pair with the ring. Okay, if you share a lone pair with the ring, then that positive charge it will be sitting on oxygen. Now the ring has no charge. It got neutral, so that's going to be stable. And with the para, okay, if we add it to the para position, the positive charge it will be here. Can we rearrange it? Yes. I will move the double bond here. Now the positive charge there. Now that the positive charge is sitting on a carbon that attached to oxygen, it can share a lone pair with this carbon. And if that one happened, again, we will get a double bond between carbon from the ring, from the benzene ring, and oxygen. And the positive charge it will be sitting on oxygen rather than carbon. So we managed to make carbon octet. Yes, the cost now having a positive charge on oxygen, but carbon is octet and doesn't have a positive charge. And we managed to distribute the positive charge, beyond the ring, okay, beyond the ring. So that one is going to drop the activation energy. So I'm going to say the activation energy in this case went down. And the same story when we added it through the ortho position. Well, with the meta position, whatever you do, you cannot put the positive charge on this carbon. And if that one does not happen, oxygen cannot help it, okay? And oxygen is an electronegative element. It will pull electron density rather than it will put electron density inside the ring. So oxygen here, oxygen group technically here is not going to be much helpful, and that's the reason we say meta. The meta substitution is going to be harder, and so I'm going to say the activation energy here goes up. And so the best one is to add it through para position or ortho position. And so again, this is the reason that we have a 67% from the ortho versus 67 from para and 30% from the ortho. Okay, because the activation energy went down, and we managed to stabilize a positive charge through sharing electron lone pair from oxygen with the ring. And beside that one, ortho has a steric effect, while para does not have any steric effect. And this is going to be the end of this lecture. And thank you.